Alright, hi you guys, and welcome back. Today we'll be talking about slope fields and the Euler's method. Okay, and basically we're going to start with talking about sketching. Okay, so here's our differential equation. Okay, and the first thing you're going to want to do is steps for sketching is make sure it is solved for y prime if you haven't already done that. Now if that is not already solved for y prime, then you need to get y alone and then start working with the actual problem into actually manipulating it so that y prime does become alone. So you need to do some differentials. Okay, now step 2 is set up on a table for x, y, and y prime, starting at origin or x equals 0 and work your way out from there. So this is just a first example. If I were to do another table, all the x's would be 1, the y's would be the same, and then start with x negative 1 and just kind of fan my way out from there. Okay, alright, so just working with this stuff is not going to be so hard because all you're going to be doing is plugging in values. Okay, and that's step number 3, is you're going to be plugging in the values into the actual differential equation. Okay, and then finding out what the slope is going to be, because this is technically the slope at that specific point. Okay, alright. Right? And then what you do is you just graph it, and you're going to do a rough graph. So graph the direction of the slope at that point, and then to find the solution, graph the point. To find the solution graph, graph at a certain point, graph the point on the slope field, and approximate your graph rating out from that point. Okay, so if we said we were going to do it from, let's say, 0, 3, something like this. Okay, all right. And then it would be something that looks like this, so we can actually see what the graph will look like. Okay, so plugging everything in, I'm going to plug in 0 for x. Okay, so this will be 4 times 0 minus 2 times negative 3. Okay, and hopefully everyone can see that that's pretty much just going to become, let me see, positive 6. So there we go. Alright, so it's 0 comma negative 3. Okay, so if I draw my point down here, so we got 1, 2, 3. Okay, my slope is actually going to be 6, so it's going to be just a simple one that looks like this. Okay, now if I graph my point, if I actually plug in this value, so this will be, well, it's always going to be 0 in the beginning because 0 is right there, and then it's going to be negative 2 times negative 2. Okay, and this is definitely going to be 4. So as you can see, it's just going to be negative 2. It's going to be the number times negative 2 just to get down here. Okay, so this one's just going to be 2, 0, negative 2, negative 4, negative 6, and negative 8. Okay. Alright, so as I'm graphing, I need to be very careful to pay attention to the fact that this slope is ever changing on here. So this one, it's going to be steep, but not as steep as the 6. Okay, same thing here. Okay, slope's going to be 0. Okay, and then as we go up, 1, 2, 3, 4. Okay, the slope's going to be going down gradually at first, a little bit steeper, a little bit steeper, and a little bit steeper like that. So as you can see, it's kind of almost like it's coming into this direction. Okay, all right, and that would be my prediction as we go. Okay, if I wanted to actually put it all in, here's what it would look like. Okay, it looks something like this. So all I would need to do is just graph it as I go. Okay, alright, so this is all over at x equals 1. Okay, so when I draw my graph, alright, I'm going to start at negative 3, so that's way down here. So this is going to be, this is actually steeper than what I've been dealing with the negative 6, so this is going to be really steep. Okay. And then it's going to get a little less steep, a little less steep, a little less steep, Okay, then we get up to 1, a little less steep. And this is obviously not the most refined method in the world to actually work with. Okay, all right. Now, the whole fifth step is to find a solution graph at the certain point. So our graph is going to be at 0, 3. Okay, so ours is going to be right here. So let me get rid of that ugly black dot. Let's make it a different color. Okay. Now, obviously, I'm graphing right here. Okay. All right. And then I'm going to follow it. So it's going to be going up this way in this direction. It looks like it's probably going to taper out. Now, obviously, I can't finish as much. Okay. And then this one would fall off and follow that. Okay. But I can actually at least start it by knowing it. Okay, now there's some really cool graphing calculators out there that will actually do slope fields for you. So please take advantage of them and then plug in your points. But if you can't find those, sketching is probably going to be the way to go. I'd probably go in a, I'd probably go out to +3 over here and -3 over here, and then sketch your field so you can get a rough idea of what it's going to look like. But, ladies and gentlemen, that's how you do slope fields. Now let's talk about Euler's method. Alright, so today we'll be we'll be continuing the idea on Euler's method. Okay, now Euler's method is an approximation method. Okay, and this is what they had to use to approximate differentials at certain points given certain pieces of information. Okay, alright, and so what we're going to be doing is you're going to be using this formula right here. Okay, y sub 1 equals y sub 0 plus the function at x sub 0, comma, t sub 0 times delta x. Okay, so as we plug in the stuff, you should be able to find it. Okay, so mainly, this is an interesting thing. There's 3 things going on here. Okay, there's delta x, which we'll find first. Okay, so delta x is, what you're going to do is you're going to take the 2 starting points. So if you notice, the starting point is 0 right here, and we're going to go up to 2. Okay, so you're going to subtract those. So 2 minus 0. Okay, and then what you're going to do is you're going to divide that by n, which is the subsection they'll give you. They'll give you the amount of sections you need to divide it up into, and n equals 8. All right, and so what this is going to turn into is 0.25. Okay, so now that we've got delta x, that is good. So we are good right here. All right, now this right here is the point from before. And in this case, we actually have y sub 0, which is just 1. Okay, so that's the exact answer. So that's when we plug in 0, we get 1. So that's what that's exactly saying, okay? Right. And what we're going to be doing is we're going to be going up by 0.25 on this. So this will start at, let me see, t sub 0 equals 0. And then the next one will be t sub 1 will be 0.25. And we'll just continue to go up in that fashion until we get to t sub 8, which is going to be 2. Okay? And that's what we're going to be plugging in every time, okay? All right, so that is the point from right before. So we'll go more into this as we go along, but this right here is pretty simple and straightforward. So this is just going to be, for our first one, it's going to be, it's going to be 0 that we plug in here. Now this is going to be the function as we plug in t's. So as we plug in each t, okay, so in other words, the subsection we are going up by, okay, we'll be plugging that in and going along as we go. Okay, and so that's the setup for t's. Now, also in the same spot, you can interchange x with t for this situation. I know that I accidentally wrote an x here and an x here, but if you change those to delta t's and a t sub 0, then that will help out too. Okay, so this is our function, and we'll be plugging in the values as we go. Okay, so technically, let me go back. Well, and then this one, shoot, I tend to screw that one up really badly. That should be a y, so that's my bad. This should be the t. Yep, and then here should be a t as well. Okay. All right. So anyways, back to the actual problem at hand. So we know when t sub 0 is 0, we know that y sub 0 is going to be 1. Okay. Then what we're going to do is, this is going to be the second one. So this is going to be y sub 1. Okay. All right. So we know that first value, setting it up. Okay. So what we're going to do is we're going to just plug in as we go. So let me use the highlighter. So we're going to plug into for this one first. And so y sub 0 is actually just 1. So I just plug in that 1. So that's pretty simple, straightforward. So 1 plus, and I'm going to use parentheses. Now what I'm going to do is I'm going to do the function at where I'm going to plug in y sub 0. Okay, so y sub 0 is 1. So I'm going to plug a y into here and then take that number and plug it in. Okay. Alright, so I'm plugging in 1, so 2 minus 2 times 1 is definitely going to be 0. So this is 0. Okay, and then I'm going times by what delta t is, which is 0.25. Okay, so that's pretty straightforward of just working with it. Okay, now for the next one of y sub 2, okay, what I'm going to do is that's going to be y sub 1 plus the function at t sub 1, comma, y sub 1 times delta t. Okay? Alright, so this is going to turn into y sub 1. Now, what my answer was I got up here was going to be 1 plus 0, which is just 1. Okay, so that's pretty straightforward. So I'm going to plug that 1 in right here. Okay? So let me point this out. So this is going to go in right here, okay? And then this is also going to go into the function and just work our way across, okay? All right. And so we're going to have this plus, okay? And now when I plug in 1 again for y, I'm going to get 0 again. So nothing really is going to change. So the really cool thing is that I'm pretty much done. It's once I get the approximation like twice, I know what the answer is going to be as I work. Okay. All right. Now it just so happens that the first two I got actually up to it. Now if you did not repeat the same number, you would just stop. You would just stop down here at y sub 8. You know. Okay, but since I got the actual number, I'm just going to go ahead and not go down to 8 because I got it repeated twice. Okay, all right. And when this happens, you can actually stop with Euler's method and know that your approximation is pretty close. Okay, all right. Once again, this is an approximation. Normally, we would just do the antiderivative of it, or I'm sorry, we would do the derivative of it, and we would work it out algebraically and do it properly that way. But right now, it's just an approximation. It's just to learn how Euler did it back in the day. So it's kind of a little bit of math history you're learning. Okay. All right, that's it for Euler's method. I'll talk to you later. Bye.